Welcome to our deep dive into interprocess communication, or IPC. For anyone building complex, high-performance systems, choosing the right IPC mechanism isn't just a detail, it's a critical architectural decision. Today, we're putting two heavyweights under the microscope: shared memory and message queues. We'll move beyond the textbook definitions to explore the nuanced performance characteristics that can make or break your application. This isn't just about which is faster in a vacuum, it's about understanding the trade-offs in latency, throughput, synchronization overhead, and scalability. By the end of this session, you'll have the insights to choose the right tool for the right job, whether you're architecting a microservices-based system, a high-frequency trading platform, or a real-time data processing pipeline. Let's get started. Simplest and, on paper, the fastest IPC method. The operating system allocates a region of RAM that multiple processes can map into their own address spaces. Think of it as a shared digital whiteboard. One process writes data, and others can instantly read it because it's all the same physical memory. There are no system calls involved in the actual data transfer, which means we bypass the kernel entirely for data exchange. This is a massive performance win. However, this raw speed comes with significant responsibilities. Since processes are accessing the same memory concurrently, you are responsible for synchronization. Without proper mechanisms like mutexes, semaphores, or locks, you'll inevitably face race conditions and data corruption. This synchronization overhead is the hidden cost of shared memory. It adds complexity to your code and can, if not implemented carefully, become a bottleneck that negates the very performance benefits you were seeking. It's a high-risk, high-reward mechanism best suited for tightly coupled processes that need to exchange large volumes of data with the lowest possible latency. Now, let's contrast that with message queues. Unlike the free-for-all of shared memory, message queues provide a structured, managed communication channel. Processes communicate by sending and receiving discrete messages to and from a queue, which is managed by the operating system kernel. Think of it as a postal service. One process drops a letter, a message, into a mailbox, the queue, and the kernel ensures its safe delivery to the recipient process when it's ready to check its mail. The key difference here is that all communication is mediated by the kernel. Every send and receive operation is a system call, which introduces inherent overhead compared to direct memory access. However, this kernel mediation provides significant benefits. Synchronization is built in. The queue handles the atomicity of sending and receiving messages, protecting you from race conditions. Messages are typically delivered in a predictable order, like FIFO, first in, first out. This model is fantastic for decoupling processes. The sender and receiver don't need to be running at the same time, making it ideal for asynchronous communication patterns and building more resilient, loosely coupled systems. So, how do they stack up in a real-world benchmark? We'll look at two key metrics: latency and throughput. Latency is the time it takes for a single piece of data to travel from one process to another. Throughput is the total amount of data we can move in a given period. For small message sizes, shared memory exhibits significantly lower latency. We're talking nanoseconds versus the microseconds required for message queues, simply because we avoid the context switch in system call overhead. As the data payload size increases, this gap narrows because the cost of the system call for message queues becomes a smaller percentage of the total transfer time. However, shared memory almost always retains a latency advantage. Now let's consider throughput. For large, continuous streams of data, shared memory is the undisputed champion. A process can write a large block of data, and another can read it with minimal overhead beyond a single synchronization event. Message queues, on the other hand, can become bottlenecked by the kernel's capacity to copy data from the sender's user space into the kernel queue and then back out to the receiver's user space. This double copy operation is the Achilles heel of message queues when it comes to raw bulk throughput. The key takeaway is this: for low latency, high volume data exchange, shared memory wins. For scenarios where decoupling, reliability, and structured messaging are more important than raw speed, message queues are superior. In conclusion, the choice between shared memory and message queues is not about finding a single best solution, but about understanding the fundamental trade-offs and aligning them with your system's architectural goals. Use shared memory when performance is the absolute, non-negotiable priority. Think of high-frequency trading, real-time video processing, or scientific computing, where processes are tightly coupled and exchange massive datasets. Be prepared to invest heavily in robust synchronization logic. Opt for message queues when building resilient, scalable, and maintainable systems. They are the backbone of microservice architectures, distributed task schedulers, and any system where processes need to communicate asynchronously and be decoupled from one another. The performance overhead is a small price to pay for the immense gain in architectural simplicity and robustness. The right choice empowers you to build systems that are not just fast, but also stable and scalable.